Well, I haven't learned any Finnish yet, so I will just say in plain English that I'm delighted to be here. And I want to thank the organizers, especially Dr. Miescke. It's really a wonderful conference. Thank you for inviting me. This is the talk I'm going to give is a little bit different from what you have been hearing, but perhaps that will will be of interest in that respect too. I've been working for a long number of years in the area of what is called multiple decision problems. It's an applied decision area, and selection and ranking is an important aspect of these problems. So let me formulate. In this case, similar work has been done for the normal model, but I'm going to talk about the binomial model here. We have 2 or 3 or more k populations, processes, binomial, and they are independent, of course. You take n1, n2, and k observations. So you see, it's not a balanced situation. And that creates the difficulty also to start with. What is the goal? The goal is to select the population which is the best, or the unknown population, which is associated with the largest theta, and to simultaneously estimate the parameter of the population that you have selected. Most of the work earlier has been, so these are 2 decision problems really. So the results in the earlier literature have treated these separately. A few years ago, about 2-3 years ago, Cohen, Sakrovich, also Esther Samuel Kahn have done some work in which they have tried to combine these 2 situations. Cohen and Sakrovich's paper, 1988, published in the Proceedings of the 4th Purdue Symposium, deals with the case of k equal to 2 and equal sample sizes for the case of normal and uniform populations. We have in an earlier paper, this is a joint work with Professor Miescke, who is a faculty member at the University of Illinois in Chicago. So we have studied a similar problem for the normal case. It is, should be pointed out that estimating the mean of the selected population is generally done in the context of what we call the natural selection rule. Natural selection rule would generally select the population with the largest observed sample mean in this case. In the case of the binomial, of course, with unequal sample sizes, this would just select this particular population from which you observe this ratio. Now, it's not at all difficult to see that the natural selection rule will not perform satisfactorily under non-symmetric models. Even in the case of course, just estimation, it overestimates the usual parameter. Very easy to see that. So here we are interested, and it of course it becomes natural to, or more reasonable to study the Bayes rules for the combined problem, incorporating some loss due to selection and estimation. So this is so we're talking about a decision theoretic formulation and solution in that context, which really, when you actually do get down to the solve the problem, what it amounts to is selecting after estimation is what happens rather than estimating after selection. So you start with the problem of selection and estimation, but in this kind of decision theoretic framework that I'm going to describe a little more, this is what happens. So the general framework would again be that you have the vector x, xi's are binomial random variables, independent, ni, theta is the parameter. That's your general likelihood function. And we are going to be talking about Bayes rules. These are the main topic of this paper. So we need not we can only concern ourselves to the non-randomized decision rules. The decision rule will be described by this notation, d vector, x vector, and it has two components corresponding to the selection and corresponding to the estimation. So you have the two parts, s of x and L of s of x, x. What is x? X is the observed value of big X. So having observed x equal to x, of course, s of x simply identifies which population is selected. It could be 1, 2, or k. And then ls of x is the estimator of that particular population. Or rather simplified, li of x, which is of course a number between 0 and 1. Well, in any decision theoretic formulation, we start with a loss function. And the general loss function that we discussed in this paper is of this nature. There are two parts. The first part is the loss due to selection, and the second part has two components product-wise. So here is the quadratic loss, theta s minus ls. Theta s is the selected population, ls is the estimate square times the b theta s. So this represents the loss at theta if population s is selected and ls is used as an estimate of theta sub s. Now in the Bayes approach, the vector of these unknown parameters k and these unknown parameters theta, we will of course denoted by capital theta, and the prior, as usual, has a density pi of theta, usual Lebesgue measure here, and the posterior density is denoted by pi theta having given x, and the marginal posterior is denoted by that function. One can easily then, within this framework, write down, prove the following lemma. I'll avoid the proofs given in this paper. So, if you can obtain, this lemma says that let Li star x minimize the expected value of b theta I. Now theta is the random variable here, and b is this part here, times of course this quantity, theta I minus Li square, having given x equal to x, for each I going between 1 to k, from 1 to k. Then, and furthermore, let s star x minimize the expected value of this whole quantity here, a of theta I plus b theta I square, given x equal to x. Then the Bayes rule for this particular situation, having observed x equal to x, is simply d star x, and it consists of these two parts, s star x and star sx x. Now, before we go further, let's discuss these loss functions in two special cases, two types of loss functions, because these will be used later on in conjunction with the conjugate beta priors that we impose on these thetas. So one is the additive loss, which has been written in these two forms, a1 theta s. So here is the best population, and here is the one selected. So you're looking at how far apart they are. And the second part of that is theta s to the power minus c, 1 minus theta s to the d, cd, both numbers are positive. And then the second, another one additive type is b1 theta s equal to some constant rho, b2 theta s equal to this quantity. And rho is a positive number, non-negative. Now, any choice of A1 or A2 actually represents loss due to selection here in this problem. B1, what B1 does here is controls the relative importance of selection and estimation, and B2 sort of adjusts the precision of the estimate L sub s to the position, to the true position of theta sub s in this interval 0 and 1. In the multiplicative loss functions that we have looked at, A3 could be taken to be 0 with B3 chosen this way, theta s to the power minus c, 1 minus theta. This is the beta type density, of course, CD being positive. So here both the parameters c and d represent any choices of loss due to selection, and they give the relative importance of selection and estimation, and of course adjustment or non-adjustment, as the case may be, of the precision of this estimate of the position of theta sub s. So now within this framework, we proceed to finding the Bayes rules explicitly for specific loss functions of these type using the independent beta priors, which is the natural conjugate family here. We restrict our attention to those situations where this product quantity, beta theta I, phi theta x, is integrable on this unit cube, and it has second moments of theta I. This is just mathematical convenience. Cases where this may not hold will not really cause any serious problems. They will occur, if at all, at the lower ends of the ranges of these x values, which we observe, x1, x2, xk. So, again, some more little notation here. We define pi tilde I x as this quantity here, tau I theta I x, divided by this integral here, where tau I theta I x is simply this particular integral over the k minus 1 cube of b theta I phi theta x d theta. What is this theta tilde? Theta tilde is the set of all these thetas, leaving out the ith component there. Then, with this theorem that we have proved is as follows. For any x, for every x equal to x, for which this quantity exists and it has second moments, the Bayes rule d star x is given by Li star x. The estimate part is given by this quantity, expected value under this thing here of theta I for all I. And S star x minimizes this big expression here, the one at the very bottom. Now, I'll be coming to some examples and so on. So even though this looks a little horrible, very long and so on, it's not all that bad. I'll skip the proof or sketch of the proof of this theorem if I have time. But let me make some remarks here concerning. Remark 1 says that the proof here proceeds component-wise, so that you can use this approach in other situations where the assumptions of the theorem hold only for some I, say not all the case, some set M of x. Furthermore, these populations I which belong to that set, for these one may just proceed as in the proof of this theorem. On the other hand, those j's which don't belong in this particular set here, one has to find the Lj star, the estimator part, which minimizes as a function of Lj this particular quantity, which minimizes this particular function here, which will of course lead to the computation of Lj star, and use that minimum value of the above quantity as a substitute for the second term, and then of course proceed to the minimization of S star x. Remark 2 says, well, that the optimum estimates Li star x, which in this case are really the usual Bayes estimates, if selection is ignored and estimation is restricted to one parameter at a point. So if you're just talking about the selection problem only, then the which one? Considered are the usual Bayes estimators, that the selection is ignored and estimation is what is the object of the problem. Okay, this is where the major thrust of the computations of this paper lies. We have computed these Bayes rules for beta priors for the simultaneous decision problem, estimation and selection, for the binomial model, of course. So we're going to compute these d star x under the general. To start with, the loss function is denoted by L theta. The second component is S, L sub S, and this loss could be additive or multiplicative type. And of course, the big thetas are independent and they follow the conjugate priors beta distributions here. Beta distribution is denoted by BE, alpha I, beta I. With this choice of the conjugate prior, things become simpler to compute, and your posterior distribution given x equal to x is again a beta, alpha I plus xi, beta I plus ni minus xi. And these are also, of course, independently distributed. Now, we look at the cases, special cases of A equal to A1. Now, I myself could use the other one, but I'll come back to specify which one was A1 and which is B equal to B1, which reduces to this particular loss function. So we are looking at this particular loss function, theta k minus theta s plus some constant rho times theta s minus ls squared. Then if you use this previous lemma, the estimates, the Bayes optima estimates are simply alpha I plus xi divided by alpha I plus beta I plus ni. These are the usual Bayes estimates, these are the optimum estimates for the single component problem. Also this quantity S star x, the selection part, is to be obtained by minimizing this long expression, which I denoted by number 1. The posterior variance of the theta sub I can be computed. It's given by this particular quantity here, 1 divided by alpha I plus beta I plus ni plus 1 times li star x times 1 minus li star x. This function, as you can see, decreases as you move away from 0.5. in either direction. So this equation 2 here causes similar behavior of 1 in the previous equation here for large values of rho larger than alpha I plus beta I plus ni plus 1. In this case, in such a case, if all estimates are close to 0, S star x would favor smaller estimates because of a smaller posterior risk due to estimation. So this means that the behavior has, in some ways, looked at it from this viewpoint, has an undesirable effect for larger values of rho, which may make the B2, the other component B2 more preferable. Also from this equation 1, one can see that the term expected value of theta largest theta k has no effect on the determination of the Bayes rule, and you could replace it maybe by a constant, say by 1, and A1 could be replaced by A2 with C equal to 0 and D equal to 1. So these are some general remarks here in this connection, some explanation here. The next case that we look at is A equal to A1 and B equal to B2, and here the Bayes rule for all, we looked at Bayes rules for situations where alpha i's and beta i's, which don't have to be bigger than 1, all you need is greater than 0, but we compute them for the cases where alpha I and beta I, both of them are bigger than 1. In this case, Li star x can be explicitly computed, no problem there, by this formula right there. And then to compute the S star x, of course, you have to minimize the quantity written in red given by equation 3. Which of course can be simplified. It actually in this case simply minimizes the quantity, this particular quantity. Now, one important case, one interesting case is when you choose alpha I and beta I, both of them equal to 1, which amounts to a non-informative prior. Then the Bayes rule turns out to be, in this case, Li star x is simply the ratio xi over ni for all I. And S star x in that case minimizes this quantity, xi minus rho divided by ni for all I. Simply say that having observed xi's, you can compute all these numbers and you choose the one which gives the minimum value. So straightforward, simple rule to apply. So remark, adjustments for the general case of positive alphas and betas are to be made as follows. I mean, cases where, alpha i's or beta i's are not necessarily greater than 1. If alpha I is less than equal to 1 and xi is 0, then Li star x is 0, and the value of this equation 3 here for that particular I is replaced by this particular quantity here. If beta I is less than equal to 1 and xi is equal to ni, then in that case Li star x is 1, and the value of 3 is to be adjusted or to be replaced by this particular equation here. Now, the last and most general case of an additive type loss that we have looked at is the choice where A is equal to A2 and B equal to B1 or B equal to B2. So using this previous theorem and the discussion so far, the preceding results concerning B, all we need to do is to find the conditional expectation of this quantity, A2 theta I, at x equal to x for all I. And this can be done, it really turns out to be, for each I, that expectation is done, but it's not it's a little long expression, as you can see here. Ratios of gamma functions are involved, provided the sum of the two quantities alpha I plus xi is bigger than c. It's this, otherwise infinity. So the Bayes rule exists if you have this condition satisfied, xi plus alpha I is bigger than c, for at least one I. So if c is less than alpha I, then the existence of the Bayes rule is guaranteed for all x, if it happens for at least one I. If you make a little further specialization, if you choose c and d to be equal, either c and d enter in that loss function, and use it equal to c and d equal to delta, which is a positive integer. Then some further the reduction, the computation becomes this one here, that particular equation 4 reduces to this particular case. So here in this case, A2 is equal to theta s to the power minus 1 raised to the power delta, so that here choice of delta equal to 1 leads to the same Bayes rule as in the case with A2 and with c equal to 1 and d equal to 0. Then the estimates in this problem, in this particular case, are the same as given at the bottom of the transparency on page 10. So there. So these will be the same things as given here. And the quantity S star x, the selection, the the part in this case has to minimize this particular function. In particular, for this, again choosing the non-informative prior, we get Li star x for this particular case to be the same ratio xi over ni for all I, and S star x is to be chosen according to the the value that minimizes this particular function. This function. In the another special case is A equal to A2, C equal to 0, and D equal to 2, combined with B equal to B2. In this case, the results are also computed here, they're given here, and S star x minimizes this particular quantity. In the multiplicative loss function type situation, we choose L theta S Ls of this type. See, this part is always there, the square part, and it's only here. So we now apply, of course, the theorem. You note that A is now identically equal to 0, and we again observe the usual properties, and then our Li star x turns out to be this particular ratio, provided again alpha I plus xi is bigger than c, otherwise it's equal to 0. So the posterior expected loss, which enters in minimization step for S star x, turns out to be this particular quantity, which is a little long, and here, the long computation here. It has two forms. Depends on if alpha I plus xi is greater than c, and then this one, and then this one. I won't read that. So in this case, if c is 0 and d equal to 2, then the computation is simple for alpha I plus xi bigger than c, and then 5, this can be used, this particular function 5 can be used to in the minimization step for S star x. The non-informative prior things do become simple again, and here the minimization is done by using this quantity, minimization for S star x. Let me give you very quickly an example, numerical example, see how this thing works. My colleague Miescke and a student of his wrote another paper in which they were just looking at the selection problem, and they have, this is not a real data problem. So you have k equal to 3 types of games are played. You play game 1 20 times, game 2 is played 40 times, and game 3 is played 60 times. And you observe the number of successes which are proportional, 9, 18, and 27. So you see 9 divided by 20 is same as 18 divided by 40, and so on. So the winning rate is 0.45 in all these cases. So that it's not clear from this information alone, if you just observe these three numbers, which of the three is the best or which of the three is preferable. So suppose we apply this non-informative prior alpha I beta I equal to 1 using the conjugate beta prior. And then for the additive loss function, this particular loss function, theta k minus theta s plus rho times this square, S star x turns out to be population number 1, and L1 star x is the 0.4545. If rho, it depends on what the rho is. You know, there is a quantity rho here. If rho is less than 0.428, then your estimator is 0.4545. And if rho is bigger than 0.4281, then S star x is 3, choose population number 3, and your estimate is 0.4516. If you have choose this kind of loss function, so theta k minus theta s here, and then you have rho times this to the power minus 1, this part is still there, then S star x is 3, population 3 for all rho, and L3 star x is actually the same number, 0.45, whereas for this particular loss function here, S star x is again 3, and L3 star x, the estimator for all rho, in this case turns out to be 0.4516. For the multiplicative loss of this kind here, and choosing these two quantities, we didn't do this example very, very thoroughly, just to give you a simple illustration here. The population 3 is chosen, and the estimator now is 0.4375. There is no rho here, C and D are already specified. So, well, you would say, well, of course, population 3 was big. In there, there was the largest number of trials. We had, I think, 60 trials were made there. So that seems to be the preferable in all these cases under these loss functions. I have some more results on the in the case what we call a fixed sample look ahead type procedure, but I think my time is run out, so I'll stop there. Thank you.